Okay, so now we're ready to carry on with our discussion about trigonometry. So let's go back to the slide. So this is the fourth part of the preliminary review of calculus, or pre-calculus, I should say. So when we left off, we were talking about positive and negative angles, but these are measured in degrees. So now we want to turn our attention to radians, which is an alternative way of measuring angles. Okay, now how does this work? Well, the bottom line is, if you want to remember how this relationship works, the most important thing is to remember that 180 degrees is pi radians. If you can remember that, you should be able to figure out any of them. Okay, so that, to me, that's the most important starting point. Um, that that right there will get you to any result that you need. Now, of course, this implies too that when we go around the circle, going through the first quadrant is 90 degrees. Try that again. To get into the first, all the way through the first quadrant, that would represent 90 degrees, which is pi over 2 radians. To come down over here, it would be 180 degrees or pi. Then down here at 2, we have 270, which is 3 pi over 2. And then to get back to the original position, that would be 360 degrees, which is 2 pi. Okay. Now, in some applications, it might be more convenient to use radians. I think most people find degrees easiest to think about because this is what we see in the real world. But radians have their place too. It's important to be able to go back and forth. It's, in a way, it's kind of like going back and forth between Celsius and Fahrenheit. It's kind of, you wish it wasn't necessary, but sometimes it is. So especially if you're traveling. So anyway. Oh, and that, by the way, that reminds me, I did mention this in the last recording. I did post this document that will almost certainly come in handy when you're working on your assignments. And you can see these are some angles, not all of them, of course. And so what they've done here is they have listed both the number of degrees and the radians. So for example, you can see right here that 60 degrees is the same thing as pi over 3 radians. And now what's going on inside these parentheses, we'll get to that in a bit, but those numbers represent the cosine of that angle and the sine. Okay, so in other words, the pairs that you're seeing there represent two pieces of information. The first one is the cosine of that angle, and the second is the sine. We're going to see why in a little while, but it helps us look up these numbers, or at least have them right in front of us. So yes, you can certainly use your calculator. One of the unfortunate things about the calculator, though, is that it doesn't, at least not that I'm aware of, have the ability to represent an answer as, let's say, radical 3 over 2. It's only going to give you the decimal equivalent. I've looked into this before and I was never able to find out a way of asking the calculator to show it to you as a radical over some other number. So, after a while, you'll start to recognize them, though, because if you look carefully at these numbers, the only radicals you'll ever see here are radical 2 and radical 3. So if you can remember that radical 2 is approximately 1.414, and radical 3 is approximately 1.7 and something. Let me just confirm that. 1.414, radical 3 is approximately 1.732. That's it. So in other words, when you get a result out of your calculator, you can check and see which radical it refers to, if there is one. Now, how could you do this on the calculator, by the way? Given that 60 degrees and pi over 3 mean the same thing, we're seeing here on the table that the cosine of 60 degrees is a half, and the sine is radical 3 over 2. Okay, now, as far as radians go, the cosine of pi over 3 radians, of course, is a half. And the sine of pi over 3 radians would therefore be radical 3 over 2. So let's say you wanted to look this up in your TI-84. So the first thing you have to know is that if you go to the upper left-hand corner, there's a little button there called mode. And if you hit the mode button, you'll see there's a lot of modes to choose from. If you scroll down to the third one from the top, it's the fourth from the top. You can see radian degree. So the way this calculator works is you have to select the one you want and then hit the enter button. So right now, let's say it's already on degree. You can leave it like that if that's what you want. If you want to switch it to radians, select the one you want with the arrow key. And make sure you hit enter, because otherwise it won't remember what you've chosen. All right, it needs that enter key to make it official. Now, oh, I just realized I have not, I need a new page here. There we go. Okay, we're good. All right, so we can confirm these by starting out. Make sure you're in the degree mode. Then literally all you have to do is type 60, and then the cosine button is directly above the left parenthesis. So just hit the cosine button, enter. Oh, I'm sorry. You have to hit cosine first. I forgot. Every calculator is a little bit different. All right, let's try that again. Cosine 60. And of course, on this calculator, every time you want a result, you have to hit the enter button. So you hit cosine 60, close parentheses, enter. And it does, in fact, come back 1. And, okay, so I'm going to add the page numbers. One of the things that annoys me to no end about Microsoft Word is that it doesn't give you page numbers unless you ask for them. I don't understand what their reasoning is. You would think that you would always want page numbers, and they should make you ask for it when you don't, but they've got it backwards, as they do so often. All right, and one more thing I need to do is save this real fast. They make a lot of strange choices. If you look at Microsoft products, at least that's my opinion. Okay, so now we're going to confirm that the sine of 60 degrees is radical 3 over 2. All right, so here's what you're going to do. The sine button, by the way, is directly above the comma. And that's going to give us, now you see, this is what I was saying, 0.866, and you're looking at it and saying, well, what is that supposed to mean? Well, like I was saying before, it is almost certainly either radical 3 over 2 or radical 2 over 2. If you look at this chart, you'll see that it looks, I'm not seeing anywhere we divide by 3. And there's only the 2 radicals. So what you do is just try both of them. So let's try radical 3. So to double check, you can type second. The x squared button has a square root above it. Then you type 3, divided by 2, enter. And yeah, it's 0.866. Now, as far as the WebAssign goes, I'm not sure if they're going to insist that you give it radicals or if they're going to insist that you give it decimals. I would imagine it'll be easier for it to ask for decimals. Um, but because then they have to provide you the right symbols to create radicals, but I don't really know. So just be ready to do it either way. Now, what about the radians? What if I want to do this? What if I want to confirm that cosine pi over 3 is in fact I have? Well, first thing you have to do is go to the radians. So you go back to the mode button, scroll down to radians, the one that says radian in degrees. Switch it over to radians with the arrow key, hit enter to make sure you're actually in the radian mode. It has to be highlighted in order for it to be in that mode. Okay, so make sure it's highlighted. Then you can just come back here. Now, the next interesting part is how do you tell it that you want pi over 3? So you're going to type cosine. Now, the pi button is found directly above the exponentiation key. So in other words, this symbol, by the way, this thing is called the caret. It's used in this calculator for exponentiation. The same thing is true in Excel, by the way. So what you're going to have to do is type cosine, open parentheses, second caret, divided by 3, close parentheses, and then enter. And it'll be a half. Okay. And of course, for cosine, sine rather, you do the same thing. Second. And it's 0.866. Okay, just like we got before. All right. So that's all you need to know, how to use the calculator for these trig functions. Now, it does also have the tangent button, but later on we'll see it does not have cotangent, it does not have cosecant, it does not have secant. We're going to see later on how that or why that is and what to do about it. Okay, so in other words, why did they leave those out? Well, we'll find out very quickly why that's happening. And it will turn out that it doesn't really matter. We can still get our answers. All right, so with all that being said, so they're giving us some standard results. 90 degrees means you're moving through the entire first quadrant, which is the same thing as pi over 2 radians. 180 degrees means you're moving across. You're still on the horizontal axis, but you're in the second quadrant. That's 180 degrees or pi radians. And then the last case, you go around the circle completely. That's 360 degrees or 2 pi radians. Now, how do you go back and forth between the two measurements? It's like I said, it's just like Celsius and Fahrenheit. So here's what you have to do to convert. Well, let's hold on a second. That's more like it. To convert from degrees to radians, multiply the number of degrees by pi over 1/8 radians. Okay, So for example, the first one they give us is 40. And so when you multiply that out, 40 divided by 180 is 0.222. That's 2 nights. And so that's how you go from degrees to radians. And then they give us another example. Now, 540, means you're going around the circle more than once. So I think they just want you to see that this approach applies no matter what the angle actually is, even if you've gone around the circle more than once. Or here they've even got a negative. As far as negative and positive goes, it's the same with degrees and with radians. Negative simply means you're going clockwise. But in each of these cases, we're multiplying the degrees by pi over 180 radians. To go the other way around, let's see. You just reverse the process, as you can probably imagine. So you're reversing it. You're multiplying by 180 over pi. So for example, let's do this one. 2 pi over 9 radians. If you notice the pi's cancel out, I've got 360 over 4. It's not, what am I saying? 360 over 9, which is 40 degrees. Okay, so, in one case, you're multiplying by pi over 180, and the second case, you're multiplying by 180 over pi to go back and forth between the two measures. All right. So, I don't know. I still think that I'm much more comfortable with degrees, but it's not difficult to go back and forth between them. Now, the basic trig functions, there are 6 of them. Now, you might remember they were all defined in terms of a right triangle, and here it is. So you've got your right triangle, and with respect to that angle theta, this is considered to be the opposite side. This is the adjacent side. This is the hypotenuse. Right now, of course, those names you haven't thought of them for a while, but those are coming back very quickly. With respect to this theta angle, this would be our opposite side. This is our adjacent. The hypotenuse is, of course, the line that connects the two sides. And so the definitions are as follows. Now, of course, we can't actually calculate them without numbers, but this is how they're done. Okay. By the way, so we'll get to this in a second, but in a minute, we'll be able to see why the calculator only shows sine, cosine, and tangent. All right, so what this tells us is that the cotangent is the inverse of the tangent. The secant is the inverse of the cosine. And the cosecant is the inverse of the sine. So that's why the calculator doesn't need to have these buttons, because if you want a cosine, all you have to do is calculate the tangent. If you need a cotangent, you can just calculate the tangent and then calculate its inverse, and you'll have the answer that you're looking for. Same thing with the secant and the cosecant. So the calculator doesn't need to have separate buttons for cotangent, secant, or cosecant because we are supposed to know how they're related to the sine, the cosine, and the tangent. And let's face it, real estate is limited on these things. They can only put so many buttons on here, so they're not going to have any buttons that are not absolutely necessary. Okay, now, by the way, I want to draw your attention to this formula here, which this formula ties together the radius of the circle with the x and the y coordinates of any point on the circle. Okay, so in other words, the equation of a circle is okay. So remember how this works with a circle. This is the diameter, and half of that is the radius. Okay, so in other words, no matter where I am on the circle, the relationship between the radius and that point is r squared equals x squared plus y squared. Or in other words, r equals the square root of x squared plus y squared. That will prove to be an important detail, as it turns out, and what comes next. Now, also, I want to remind you that, or if you haven't seen this before, this formula is actually a special case of the distance formula. You can actually calculate the distance between any 2 points by using this formula. It just so happens here that the distance itself is the radius. And let's see. So what they're doing here is they're rewriting these functions in terms of the radius. Okay, so you can use these instead if you want to, but I think, I don't know about you, but I prefer these formulas. Now, there's a whole slew of these formulas, and I don't think anyone realistically expects you to memorize them. The book probably has a table in there somewhere where they're all listed. Um, let me just check something out here. There's this great website that I showed everyone the other day called MAT1500. It might have a list like this. Okay, so these relationships, by the way, are sometimes called the reciprocal identities. The definitions of cosecant, secant, and cotangent. Um, there's so many relationships that you could potentially go through here. We have the double angle formulas, half angle formulas, the Pythagorean identities. We'll be looking at this one in a bit. Um, there's it's just unbelievable how many different formulas are available for these trig functions. But the only one you might stick in your memory really, besides the definitions, is maybe this one, maybe stuck in your memory from an earlier class. This one you see, you run into this fairly often in trig, or either that or you use it to help simplify your results. So, but here they are. Um, ooh, I'm not sure if they have the odd even ones. But anyway, so there's a whole slew of these. And the reason why it matters is because if you're using a trig equation of some kind, often you can use these identities to help you reduce the problem to something more manageable and end up with a much simpler result than you would get without these formulas. So here they're putting together a little chart so you can see some of these angles. These diagrams are there. They're trying to prove why these cosines and sines have the values that they do. They're doing it in terms of geometry. So we don't have to derive any of these. This table, though, might come in handy. They're showing us how the signs are for these three basic trig functions in each of the four quadrants. Okay, so like for example, in the first quadrant, they're all positive, and the second quadrant, this cosine and the tangent are negatives. In the third quadrant, the first two are negative, the tangent is positive. And in the last case, in the fourth quadrant, only the cosine is positive. Sometimes that might help you simplify a result. Now, of course, a lot of this was more important when there were no calculators, but, it's still important to understand how these relationships work. So, all right, anyway, you know what? I'll tell you what. I would like to get started with Calc 1. Okay, so I think we've had enough trig for one day. Why don't we jump ahead and take a look at our very first discussion about actual Calculus 1 in Chapter 1. Let's go back to Brightspace and find Chapter 1. Oh, I thought I had it open, maybe not. All right, here we go. At long last, we get to start Calc 1. We're going to introduce the concept of the limit. Now, the limit is an awfully important concept, and it's going to be used to derive results that we'll use throughout the course. But the limit is itself a very important concept. So we want to start by learning what a limit is and how is it useful to us. So all right, they're getting a little philosophical here, but let's start here. All right, now everyone remembers what a tangent line is. A tangent line is a straight line that touches a curve at exactly one point. And often the slope of that tangent line is an important result that we need for some application or other. It often is something that we need. We'll see later on that we can use it to find, for example, the maximum value of a function or the minimum value. So the tangent line is the one where it touches once. And in case you've forgotten, um, tangent line touches a curve at exactly one point. And often our motivation is to find the slope of that tangent line because it provides us with some very important information. Sometimes though we have a line rather, that cuts through a curve at 2 points. And if that happens, it's referred to as a secant line. So for example, you might have something like this. And we may be interested in the slope of this tangent line, or we may simply be interested in the points where it crosses that curve. Okay, that depends on the application. So we need to be able to find both a secant line and a tangent line. So, oh yeah, here it is. So they're just explaining to us, you can see here that this blue line is a secant line because it crosses the curve twice. Now, what they're showing us here is that based on this diagram, hold on, let me get this. All right, so we don't need this anymore. All right, here we go. So if you look at this diagram one more time, you'll see, let me actually copy this onto my document here. So there's 2 points, P and Q, we're calling them. And the first one has the X coordinate C, Y coordinate F of C. And up here, what they're saying here is that the difference between the two is this delta X. Okay, so in other words, if let's say C is 2 and delta X is 1, then C plus delta X would of course be 3. So the change between the X coordinates is defined by this delta X. And the delta X simply means it's a relatively small change in X. The difference between the Y coordinates is F of C plus delta X is the second point. The first point was F of C. So the difference between the X coordinates is delta X. It's a simple additive. All we're doing is adding delta X to C. But the difference between the Y coordinates, we don't know without knowing the function. So we're going to write it as F of C plus delta X minus F of C. Okay. So we're implicitly assuming that we're moving from this point down here to this one. It doesn't really matter which is the starting point, which is the ending. These results will be the same either way. But it's important for us to know that the slope of this tangent line would therefore be, not tangent, I'm sorry, secant line. Is, remember, informally, the rise over the run. And that means we have F of C plus delta X minus F of C all divided by delta X. So if we knew this information, if we knew what the function was, if we knew the size of delta x, the value of c, we could calculate the exact value of the slope of the secant line. Okay, and there it is right there. That, you notice how they're writing MSEC, that stands for slope of secant line. Okay, so it's f of c plus delta x minus f of c, all divided by delta x. Now, here's what they're going to tell us. Imagine that the delta x gets smaller. So notice we start out here, and we've got this curve. And got our secant line. If I were to reduce the size of delta x with the same function, say now I've got c, and let's say I'm here on that c plus delta x. What they're getting at here is that if delta x continues to shrink, let's see. I know I have a symbol for delta here somewhere. Let me go find it. Here it is. The slope of the secant line gets closer and closer to the slope of a tangent line where x equals c. Okay, so in other words, let's see if I can draw this properly. Yeah, let's go back to black here. I'll tell you what, let's pick a different color for the tangent. So as c plus delta x gets closer and closer, let's say here, well, they're going to get closer and closer to each other. Okay, so when c plus delta x are very far apart, if you notice, in fact, you know what, I could even put this back up here. They're not very close to each other at all, are they? In the first case, when delta x is fairly large, um, the two slopes are not very close at all. And then as we keep shrinking up the delta x, the slopes are getting closer and closer to each other. All right. So, okay, so that's where this, and that's what this graph is trying to show us. They're showing us all these different secant lines, and what they're trying to get at here is that they're getting flatter and flatter. In other words, eventually, if we have, imagine that the difference between the 2 points, delta x is infinitesimally small, then the two lines will be more or less identical to each other. So now they're kind of leaving us hanging here. They're not telling us why this is so important, but this is at the heart and soul of what a limit is. Okay, so you'll see that as we get further into this chapter. It's you have one variable that's getting really small, and we're trying to see what the impact is on another variable. So here they're bringing us up another topic where we may want to find the area under a curve, but where the function is very complicated. Now, if we had a rectangle or something, this would be a piece of cake. But if you notice here, they've got this function, and we're looking at it between points A and B, and we'd like to know what is the area under this curve, the shaded area between A and B. Well, here's what we could do to at least approximate it. We could create a series of rectangles and use the areas of those rectangles to approximate at least the area under the curve. Now you can see in the first case, the results are going to be not terribly accurate because the rectangles are very wide. The diagram on the right, as we shrink up the widths of these rectangles, and there are more and more of them, you can see that the area is getting closer. The purple is getting closer to the orange. So if we imagine that we keep shrinking up the width of the rectangles, eventually the rectangles will match the area under the curve. So let's see, here they got a very specific example. Now, they would like us to see, though, that we can actually go about this in two equivalent ways. If you notice, there's two different approaches. These two sets of rectangles on the left and the right have the same widths. What's different is the heights. How do you define the heights of these rectangles? So what's happening on this side is we have these intervals. And these are the same x's. Let's think of this as x0, x0, x1, x2, x3, x4, x5. So each rectangle is the area between, let's say, x1 and x2, x2 and x3, et cetera, et cetera. On the left, the height of the rectangle is coming from these points. Over here, it's coming from these points. Now, you can see that neither one of these is correct. The one on the left, the area of the rectangles is too small, and the one on the right, the area of the rectangles is too large. But if we keep shrinking up the areas of these rectangles, they'll both eventually meet in the middle and give us the correct area. So let's see, what are they doing here? Oh my God, that was the first section. All right, let me jump on to the second section. So they're giving us a lot of useful, helpful hints as to what's coming, but so far they haven't tied a full example together. So let's go back and look at section 1.2. See where all this is taking us. By the way, it all seems very bizarre and mysterious right now, but you'll see limits are a very straightforward concept. whenever they're introducing something new here, they always tend to be very formal about it and give us a lot of theoretical results. But you'll see pretty quickly that calculating limits is not that big of a deal. Now, here's a function. Now, by the way, for something like this, let's go look at Symbol Lab before we go any further. Let's see what this is all about. Now, you can clearly see, because you have x minus 1 in the denominator, that we may not let x equal 1. The domain does not include x equals 1. Because otherwise, it would be divided by 0. All right, so what do we have here? X cubed minus 1 over x minus 1. No, that's interesting. Um, well, you know what? You notice what must have happened is it must have reduced to a simple quadratic equation. Um, See now, I'm surprised that the Symbol Lab didn't. See, I think I'll tell you what, if you were to do this ratio, calculate this ratio, you might remember from pre-calc, that there's a way you can divide one polynomial into another one using a process called long division. And that's how you can figure out if the denominator is a factor of the numerator. So I'm going to run through this real fast. Um, there it is. So what ended up happening was that this x minus 1 divides evenly into x cubed minus 1. So what Symbolab is actually showing you here is the x squared plus x plus 1. Now, unfortunately, though, that's not exactly what we need, because um, it was clear from the original function that we did not want to substitute x equals 1 into this function. So the way they normally do this is show this with a graph like this is at the point that would have led to division by 0. Well, actually, maybe they did. Hold on a second. It's possible that I was zoomed in too close to it. Let me try this one more time. Because there's supposed to be a hole in the graph at x equals 1 to indicate that we may not substitute that value into this function. Let me try this one more time. It's possible that I overlooked something. Oh no, there it is. What happened? I didn't see that before. Was that? All right, maybe I didn't look at it carefully enough, but you can see there's this tiny little hole here. All right, so my faith in Symbolab has been restored. All right, here we go. There needs to be a hole here. It even says 1, 3 is undefined, because x equals 1 is not part of the domain, which means we have a hole here. And so the function is not defined when x equals 1. It's defined everywhere else. It's a well-behaved function. But right here, we have a problem. So now what they want us to see is that if we get closer and closer to that point, let's say, what if I want to know the value of the function when, let me just try a few cases. Let's say x is getting closer to 1, and we're approaching from the smaller values. We start with, let's say, x equals 0. Fine. When x equals, let's say, a half, that's going to give us, oh, okay, hold on. I did something wrong. Negative 0.58, it looks like. No, that can't be right. It's positive 0.58. So in the slides, they're giving us this little chart, so we don't have to go through this trouble. What they want you to see is this. If I evaluate the function with x's that are smaller than 1, let's say starting with these numbers here, we move up. As the x's increase, we're getting closer and closer to x equals 1. Okay, so here they're trying 0.75, 0.9, 0.99, 0.999. We say that x is approaching 1 from the left, meaning it's moving this way towards the larger numbers. So as we move x from the smaller numbers to the larger numbers, we get very, very close to 1. We don't ever actually go to 1 because we know that's undefined. Now, if we do the same thing from the right, meaning we start with the larger x's and work our way down to the smaller x's, we say that x is approaching from the right. Specifically here, it's approaching 1 from the right. Now, we don't have time to go through and recalculate the function for all of these different x's, but what they want you to see is that here we're getting closer and closer and closer to 3, and here we're getting the same thing. So from coming from the left, the function's value is growing and getting very close to 3. Coming from the right, the values are larger and they're getting smaller. And eventually they're getting awfully close to 3. And in fact, it says it down here, f of x approaches 3 from the left. It approaches 3 from the right. So we say, in spite of the fact that there's a huge hole here, that let's see. Oh, here it is. In spite of the fact that there's a huge hole here, we say that the limit of f of x as x approaches 1 In this case, it's equal to 3. So in English, that this means, we pronounce this, the limit of f of x as x approaches 1. That little arrow means x is getting closer and closer to 1. It could be coming from either side, by the way, with this notation. And this is equal to 3. So that while there's a hole here, the point of the limit is that we're getting infinitesimally close to that point. We're not actually touching it. So we're going to get awfully, awfully close to 3 without ever quite reaching it. And so we call that the limit. It's like, you may have heard about this problem in probability theory where you shoot an arrow at a target. The arrow covers half the distance every second. When does the arrow actually hit the target? The answer is never. Okay, it's getting close. It's converging towards the target. The limit of the arrow's flight is the target, but it never actually touches the target. Okay, and that's what's happening here. Now, by the way, notation-wise, if we're only interested in what's happening as x approaches from the left to the right, there's this slightly different way of writing that. So that little negative there means we're approaching from the left. And when we write it like this, that means the limit of f of x as x approaches from the right, meaning from the larger numbers. Now we're going to see later on that if these two are equal to each other, then we have a limit. And in this case, that limit is 3. If they're different from each other, then the limit does not exist. In other words, it has to be the same coming from either direction. So the limit here is 3. It probably says it here. Maybe not. All right, we could probably ask for it though. Now, if there wasn't a hole, now interesting thing is that without the hole, it would still be 3. Okay, in other words, if we had remember we saw before this ratio equals x squared plus x minus 1. If that was the actual function, there would have been no discontinuity and the limit would still be 3. So the existence of this hole does not mean that we can't have a limit. It can still have a limit. But a lot of the cases we'll be looking at, we'll be having these smooth continuous curves with no discontinuities, and then the limits are very easy to find. The challenge comes with these functions that have gaps in them or asymptotes or other bizarre things going on. But the idea of the limit is that there's some value y that we're getting very, very close to as x approaches a certain value from either side. So anyway, so now we just barely started to touch on this topic, and we have a long way to go with limits. So we'll come back here and we'll revisit all of these concepts, and we'll kind of go through them one more time just to make sure everyone understands what in the world is going on, because it probably seems very bizarre and abstract right now. But you'll see pretty quickly that a lot of limits are very straightforward to calculate. And here they're just reminding you that now, like you see here, if you notice, there's not only a discontinuity, but the function itself, it's a piecewise function that has two different sections, and the value that the function takes when we approach from the left is different than from the right. And in that case, then we say that the function does not have a limit at all. It does not exist. So we'll consider all these cases. But I think for now, we have to knock it off and save this discussion for next time. And so once we get through all of the definitions, And these definitions can get a little intense. We'll spend most of our time actually calculating limits, and you'll see it's not that difficult for most cases. So that's good news, right? All right, so I'll just stop it here, and I'll see you all next time.